Jackson and Megan. There's one. So hopefully you guys have noticed what day today is in the 12 days of Christmas. Have you figured it out?
Yeah.
What?
Favorite jersey.
Favorite team. Favorite team day.
That's what.
That's why it's not just all football.
Well.
You notice that Miss Ramirez is wearing baseball.
Yeah. She said it's favorite jersey day.
It's favorite team day. So yeah, that. Jackson must be having some problems with his internet. As a reminder, guys, make sure you bring back that Christmas letter back. Okay?
Christmas party letter?
Christmas party letter. Jackson left.
And the money.
And the money, please.
That's probably why he didn't come yesterday. He's having technical difficulties.
Mike, but he got all the work done too, which was good. Okay, so we're still investigating the relationship between energy and speed. We're not using the little crash test cars today, and we're not using a soccer ball. You see those things are gone, and look, my table is nice and clean because Allie finished up her test yesterday, and she was my last person to finish my test. That part of my board is cleaned up, which is nice. Aaliyah McGill, have you returned your papers 3 through 9 to Miss Ramirez yet? Neither's my Riley. So I've got still 2 more people who need to return back pages 3 through 9. Sir Legend has been gone for a week and a half. He returned today, and the first thing he did was hand me pages 3 through 9. That's dedication to getting his job done. Meanwhile, I've got people who are here every day and still don't turn in what they're supposed to turn in. Right, Orange Bow? Are we going to alleviate that? Have you brought in your Christmas letter yet? Are you going to be the reason your whole class doesn't get to watch Jingle Jangle? Y'all, I'm not getting much inspiration here. Raise your hand if you want to watch the movie Jingle Jangle.
My mom said it's really good.
It is very sweet. It's very inspiring to everybody.
I watched it, but I didn't
I've watched it and it's really good.
It is, and I would really like all 3 of my 4th grade classes to be able to watch it.
I may have watched it.
So, I need everybody to bring back the letter. Signed. Got it? It's due back by this Friday. Clear? It has to be signed by a parental unit. And I say parental unit, you guys have heard my spiel on this before, because not everybody lives with mom and dad. Got it?
Parent or guardian.
Parent, guardian, aunt, uncle, whomever you go home to at night, that's who signs it. Clear?
Whoever's there.
Okay, so today we're going to continue looking at the phenomenon question, what is the relationship between energy and speed? That's why I left it up there in the same dark purple pen. It probably looks like to you guys black, but it's not. It's dark purple. What is the relationship between energy and speed? We're using different materials to explore that question. Okay? And so that my materials don't go rolling out in the hallway today, we're going to shut the door again.
Yay!
Santa doesn't need to see a ball rolling out in the hallway. Okay, because it's going to be a ball, but it's going to be a small steel ball today.
Santa does not want to get hit.
Yeah, you don't want to get it. And you guys, we already discovered yesterday that my floor in here is not level, is it?
No.
So it's probably going to roll to the side. Just heads up.
Wait,
I didn't know it was
It might. Well, my 3rd block, it kept rolling towards the wall. Okay, so what did we discover yesterday? When we give something more energy, what does that do to its speed?
it makes it fast.
It makes the speed go faster, right?
And
Makes-
farther.
Yes, it makes it go faster though, and farther. Yeah. Yeah. So if we kick the soccer ball harder, it made it do what?
Go faster and
Go
farther.
faster and farther.
And farther. But
Didn't that thing just beat?
Yeah.
So second block, Travis was so scared of the ball causing harm that he just would not kick the ball hard enough. I said, would you please kick the ball? And I had to get him to put his foot under the ball and kick it to get it to go to the door, because I needed someone to kick that ball hard enough to get the ball to go to the door. So he did. He got his foot under the ball a little bit and kicked it hard enough to get it to the door. So it came off the floor about that far, just for a minute, and then it dropped back down. But it got it to the door. The ball moved a lot faster.
So it was like Ethan and the crank.
He got it off the floor. It moved faster. It didn't hurt anything, but it moved faster, which is what I needed everybody to see, that the ball definitely moved faster. Now, yesterday afternoon, who was it? Lakin was the one kicking the ball. You could barely tell it was moving faster because she was so afraid of hurting something. I told my husband about the experiment yesterday afternoon. He was just chuckling. I said, my kids are so scared of hurting something in my room. He said, well, it's better than breaking something. I said, yes. Because like I said, one kid threw a football one time and smacked the mess out of my projector. Yeah, I don't need my my expensive equipment getting torn up. But we're going to see today with smaller materials that more energy input into the system means the object will move faster. Okay, makes sense? Like when a person puts their foot down heavier on the accelerator, what does the car do? It moves faster. That's why someone jokes about a person, if they're going fast, they have a lead foot. Y'all understand that reference? No? If a person puts their foot down heavier on the accelerator, the car goes faster. It's also called jackrabbiting from a light. In other words, they floor it at a stoplight when it turns green. Yeah. That's called sucking down the gas on a car. Because you're really not going to beat anybody because you still got a whole bunch of red lights. You got to stop at every red light. Remember us talking about coming from Bossier to Shreveport? You're not going to get here.
6 minutes.
I said this to second and third block. I don't know how much we discussed this yesterday. If you have a race car driving 200 miles an hour and a regular car driving 60 miles an hour from Bossier into Shreveport, is the race car really going to be able to make it in 6 minutes from Bossier to Shreveport? Why not?
They get pulled over. Red mark.
Red
The person
lights.
who would beat was the person that was actually going
Bad
fast.
traffic.
Red lights, bad traffic,
Cops.
policemen. There's a lot of other things that you have to contend with, real life situations, right? Now, if you're on a racetrack, closed racetrack, and you're legally entitled to be racing, yes, that 200 mile per hour race car is going to lap that 60 mile an hour car, right? Trains. If you're on roads like these, there's a lot of things that are going to slow you down. Everybody gets that, right? School zones, if you're going through that at that time. Okay, so when we gave the cars yesterday more energy by pulling them back more, they went faster and farther, right? They moved more. When we put more energy into the soccer ball by kicking it harder, it rolled farther and faster, especially with Travis. He got it to the door, like halfway up the door. When we kicked the ball softly, it didn't even make it to where Michaela was, right?
No.
It like made it to the trash can, right?
They made it to about.
When someone kicked it softly, it didn't go that far. Not where the trash can is now, but where we had it yesterday.
Oh, yeah.
It didn't go that far.
I thought you would like.
No, I had to move that because the Google, the Chromebook cart's going to go over there.
Where Ricardo is.
Yes, the trash can was close to Ricardo, maybe a little farther. And that's about as far as the ball went when we kicked it softly yesterday. So do you remember at the end of the lesson yesterday, we talked about fair test design?
Oh yeah, I thought we were gonna do it today.
That's what we're going to do today. So we have to set up our investigation so that they're fair test designs. We can't set up a design where you have, let's pretend this is a ruler, where you would have a ball rolling down a ruler from this height, and then you would have a ball rolling down a ruler from that height. Why not?
Because the ball would drop because of the height.
This is taller, isn't it?
So that
And height of the book has to do with how fast it's going to roll, doesn't it?
and how stable, like how steady.
And how big it is?
Think about it. With a roller coaster, who in here's ridden? Stop talking over at table 3. Who in here's ridden a roller coaster?
It was for the
I'm just it's
If you haven't ridden one, you've seen one.
Oh, I have.
You understand how a roller coaster works, hands down.
Scared.
How fast that roller coaster drops has to do with how high the hill is right before the drop, right?
Yes.
So if you're saying I rode that kiddie roller coaster and it was just as scary as the Texas Giant,
I do the one in Disney World, the big old mountain ride.
they're not the same, are they?
No.
Because one might have a 10-foot drop and one might have a 220-foot drop. It's not the same design, is it?
No.
Look, this is a 1-inch decline on this pencil. This is a 1/4 inch decline on the pencil. So if I had something roll down the pencil, it's not going to roll down very fast. If I had something roll down this pencil, it's going to roll down faster. Does everybody see that? So when a test is being designed, the thing that you're testing has to be the only thing that changes.
But
Does
if
that
it's-
make sense?
If it's heavy, if the things are heavy, like the things that you're in is heavy and we're going up the thing,
But
it can go faster.
But you would use the same mass object on both things. You have to keep everything the same except the one thing you're testing. For example, me with my migraines, my doctor can come up with all different kinds of solutions for migraines, but she can't change them all at one time. She can only change one thing every 3 or 4 months. Otherwise, she's not sure which thing worked. So it's frustrating for me because I'm in pain for months and months and months. I've had these migraines now for 8 years, every day. But they can only change one thing every so many months because it has to be a fair test design.
So
You can only change one variable at a time because they have to know what works. What is the thing that affects it? That's how medicine rolls too, because it's science, right? They have to know what works and what doesn't. So they can only change one thing at a time. Make sense? Okay. All right. So we're going to design a fair test investigation. And I'm going to be honest with you guys, because when am I not? As Miss Galt puts it, real. I'm always very real. They want you guys to come up with your own investigation. But nowhere on the LEAP test would they have you come up with your own investigation. They would not have you make your own investigation. They would not have you come up with your own lab. They just wouldn't. And honestly, that would take you 30 minutes and you still would end up more confused. So just like yesterday, I'm going to tell you what we're going to do because I have the materials. It makes no sense for you to flounder and try to figure out a lab and then say at the end, oh, well, this is what we're going to do. That's a waste of your time. Okay? That's real. What is it, Hunter? Yep, don't worry about it. Okay, so is this a reasonable thing to say? When we give an object more energy, it moves faster.
Yes.
We saw that yesterday, didn't we?
Yes.
We gave the car more energy by backing it up more. It moved faster. And it moved farther, right? Okay. So the things we're going to use to do this lab.
Wait, this is the weird one we were talking about.
Pencil. Instead of using a 1-inch book, you guys might have noticed, it's weird to say this. I know we're in a school, but we just don't use textbooks anymore, do we? It's Chromebooks, exactly. It said it wanted me to use a 1-inch textbook, but the reality is we just don't use them.
No.
We use trade books, but my trade books aren't an inch thick. We're going to use this in place of a book. It doesn't collapse easily because the way it's designed. It's over an inch, so it should make it really roll well. Okay, so this is going to be used in place of our book.
What's on a roll?
This ruler, it has a groove in the middle that will help the ball roll down it.
Yes, that's a great idea.
These are steel balls. They're heavy, so it's in 2 different bags. The bag within a bag.
Yes. I've seen those before.
They're ball bearings.
Don't they help you like calm down?
I would recommend these.
Like
Oh, it is.
Can I see?
They're dense. They're very, very dense.
Can I see how?
Okay, so this is going to be the ball bearing that we use. It's a 1-inch steel ball bearing. It's heavy. It's cold. That's going to be the thing that we're using to test. Okay, it's
Looks
very
like a Mardi
dense.
Gras bead.
Only if you want to kill someone.
Okay.
I mean, that could definitely kill them.
What if it hit you in the eye?
It's like if you hit somebody in the head with this, it would go through their head.
Huh? What?
Yeah, right through.
Like it will go through the brain.
Yeah.
Hit me in the
And
head.
a timer. Okay, one person in the room is going to work the timer.
Oh.
We're going to do, hold on. We're going to do this just like we did last year because this would have been too chaotic to have multiple groups doing this with the timer. So it's going to be one lab going on for the whole class, and the whole class will record data. And then I record data on that notebook and on another sheet of paper, front for one class, back for the other class, and we compare the 3 pieces of data through the day. Okay. So I have 3 of these. I can't spray them with Lysol, so 1 for first block, 1 for second block, 1 for third block. Okay. Actually, yes, you will. You're good with precision, so yeah, you will. Last year I had a girl who did it. Yeah. I need someone to I don't know whether we use these today or whether we'll use these Thursday. This is a catch. This I have to look on the experiment. But this will get pushed by the ball. This is the transference of energy. You know, we talked about when the cars hit another car, it transfers energy. This is when it transfers energy. Yes, ma'am.
It's like your thing where it knocks the ball over by the window.
This, I don't know if this is today's or Thursday's, but whichever one of the labs, the ball hits this, like catches it and pushes it back. And we measure how much it pushes this back. And I think this is Thursday's. Tomorrow we have conceptual checkpoint. Conceptual checkpoint tomorrow as well.
Another
We
one
had a
Yeah.
conceptual checkpoint last
Yep, I know.
on Monday.
Okay, so your ingredients are what I just showed you. The box that we're using in place of the book, the ball, the ruler with a groove in it, and the timer. Now, it wants us to use a meter stick to measure how far it went, but actually, you see these floor tiles? Each floor tile is 12 inches. So you measure how many floor tiles it goes across. Let's say it goes 10 floor tiles. That's 10 feet. And then you use a measuring stick and you see how many inches beyond the tile it went. So if it went 10 tiles plus 3 inches, it went 10 feet, 3 inches. Does that make sense?
Yeah.
All right. It's a faster way of doing it than laying out the sticks. Does that make sense? Okay. So we have to do something first. And this is the craziest thing, but it demonstrates something. This is not my lab. This is not me coming up with this. Unfortunately, my friends that are virtual won't be able to see this part. Why is live image not coming up? Okay. All right. Image mate. Let me see if image mate will come up now. Image mate. Share. Share, stop share. Image mate. I had to show my students this last year because I knew they wouldn't believe me. We have to amend it a little bit because your old teacher here has had almost 200 grand worth of surgery on her neck. So I'm not the linebacker that you're going to run into. I want you to look at this. Before students design their investigations, demonstrate a race between two students to clarify how to quantify speed. Stand at one end of the classroom and explain that when you say go, student A will run to you quickly while student B will walk to you slowly. At the end of class, students are supposed to both run into me and tackle me. To see, yeah, exactly, Kayla. Your face, that's exactly what I thought too. To see transfer of energy. Now, I'm going to point right back to this again. I don't care what Mr. Williams says, and I'm not supposed to mention this, but if this has much energy put into it, it will completely break because it's brittle. Titanium is very hard, but once it has a quick transfer of energy, it will completely break. It will shatter. So it should be fatal. No, we're going to do it the same way we did last year. I put a desk out in front of me, and my students crashed into the desk because I'm not dying.
Okay, this is fun. Okay.
Yeah.
Oh,
so when my students go into the desk, you get to see how you transfer energy to the desk.
Energy transfer to.
I'm not standing up next to the desk. I'll have somebody else stand behind the desk. Hold on. Point is, I don't want anybody hurt because Mr. Williams is like, surely you didn't have your kids do this. I said, well, it's part of the test. 15 minutes devoted to it.
Yeah. It sounds fun. We're gonna have an awesome day today.
You might get a little bruised.
Okay.
I'm letting y'all know. I'm letting you know you might get bruised. Ricardo, you and Bryson were the two that I picked out yesterday, remember? That's why I was asking you about this. So this one's perfectly safe because y'all don't run into me on this one. This one is just designing a fair test, which involves the two of you, starting on the same place and ending at the same place, me. Okay. One person's running, one person's walking the whole way, and neither one of you are actually going to crash into me, or I will knock you down. Clear? We got it?
Sure.
Because I will accidentally on purpose knock you to the ground.
Accidentally on purpose.
Okay, so Megan, sorry you can't see this because it's pretty funny. But you catch on to what we're about to do, right? No, you're about to run in.
Yes, ma'am.
All right, Ricardo, come on. All right, so one of you is gonna stand right here, one of you is gonna stand right here. No, it's not right there.
Everybody gets back into the jar.
All right. No, you're not. Yes, this time Bryson's running, Ricardo's walking. Bryson, I need you to step over. Right? Who used up more energy? Who used up less energy? Ricardo.
Now who is crashing into their table? Me. No, I'm the biggest.
Nobody yet.
I'm Santa Claus. Me.
No, you're not.
Yes, he is.
Oh, insane. Oh, music.
I'm the strongest. I can do it.
Okay. Can we get to the lesson? Guys, I'm trying to get you ready for tomorrow's quiz.
Tomorrow's quiz.
Did I not tell you you have a conceptual checkpoint?
Oh, yeah. Yes, you
Sit. Who was faster, Bryson or?
Bryson.
Okay. What does faster mean?
It means you didn't A use more energy.
Bryson used more energy, but what does faster mean? Do they both go the same distance? No, listen to me. Listen to me. Stop repeating what other people are saying and think for yourself. Do they both go the same distance?
Yes.
Yes. Do they both go in the same time?
Yeah.
No. So what does faster mean?
It means different times the same distances.
Yes. So does that mean slower time, more slower time in the same distance, or less fast? Try to say it right.
More.
Less time, same distance, or more time, same distance? Less time, same distance. So faster means more speed, right? What was the same for both students?
The
The distance.
Where they where they started.
Where they started. What else?
The stop.
What?
The stop.
When they started. Y'all both started at the same time, right, Ricardo?
No.
You're supposed to.
Well, he went back a little farther than Ricardo.
You didn't start at the same time?
Yes, we did.
He was further back than Ricardo.
But Ricardo was a bit further back than Bryson. No,
Bryson
further back.
Y'all are supposed to start from the same place at the same time.
In the same Colorado. We were at the same spot.
Okay, so which student had a slower speed? Okay. So speed is the distance an object moves in a certain speed is the distance an object moves in a certain amount of time. No. Distance an object moves in a certain amount of time. All right, so that's right here. Speed is the distance an object moves in a certain amount of time. When measuring and comparing speeds, the distance an object moves across the room during the race and the time it takes to travel that distance, how long it took the student to cross the room must be considered. So you have to use a stopwatch to measure how long it takes the object to travel, and you have to measure the distance that the person covered. Okay. The ball bearing. How can we give different amounts of energy to that ball bearing before we drop it on that ruler? So here's the box. That's the box that we're going to use to make the incline. Here's the ruler. That's what's going to form the incline. How can we give different amounts of energy to this ball? Okay, look. Here's just letting it go. If I release it at the 2-inch, is that the same as releasing it at the 5-inch?
No.
How's it different?
Because one is slower because you put it at a different start.
It is at a different angle. Watch how far it goes across my table. From 2-inch. It's like I'm playing pinball. Versus 5-inch. The 5-inch, does it look like it hit it as hard?
No.
Look at it when I run it from 7-inch. It looks slower, doesn't it?
So it is the longer angle.
It's going farther because it's closer to the end, but it's not going faster. So I don't know how it's
No, it
Look.
goes faster and farther. Look. Yeah.
Starting it from the 1 inch,
It goes faster.
it goes faster, doesn't it?
And it hits harder.
So can I change the amount of energy the ball has according to where I put it on the ruler?
Yes.
Okay. What else could I do to the ball to change the energy the ball has? Because all those times I was just putting the ball on the ruler. Was I pushing it? No, I was just putting it on there. I could push it
And give it energy
by pushing it. So that time I pushed it and it really pushed hard.
It did.
I bet I can ramp it off and lose it underneath the thing down there, but these, I don't even want to know what that would cost.
That hits to it. Lower to it.
Well, maybe you should.
Trust me, your mom doesn't want to be trying to find this, or your grandma.
Maybe you should take stuff off so it like goes farther.
No, because then it would get lost.
But do 2 balls at a time.
No, that would probably be like physically impossible.
Yes, no, it wouldn't. Oh,
That 6, starting at the 6 when I pushed it, had as much force on it when it hit the book as when it had the 2, when I started at the 2. So you can push it and give it a lot more energy. So are there ways to change the amount of energy on the ball?
yes.
Okay.
So that could break the floor.
Yes, it could. So are there therefore ways to make this an unfair test?
Yes. Yes.
So if you were to push the ball,
It would
that
be
makes it an
unfair.
unfair test.
But if you
So whoever's doing this test in the front of the room needs to make sure they're not pushing the ball. And that they're noticing where they're putting the ball on this ruler, because it's going to make a big difference.
How fast is that more?
Okay. Which position did the object have more energy? When it was up here around the closer to the box, or when it was down here? Closer up here, right? What if I had smaller ball bearings?
It would probably go
faster.
faster. No. Because
The weight would be different, wouldn't it?
Yeah.
So if I had something lighter, it might go slower because it wouldn't have as much
Wait.
mass to it.
Just go down.
Okay, so your notebook right here. We need to record the investigation question, which is how can giving an object more energy and of course it's being weird with the light. It is.
What
19.
How to get an object more?
How can giving an object more energy affect its speed?
It can affect it.
Well, that's what you have to copy is that question. And then on the bottom, you need to copy these steps. Number 1 says conduct the investigation on the floor. Number 2, use a box that is about 3 inches tall. That's what the 2 little marks mean. And put it flat on the floor. Lean a ruler flat side down on the box to create a ramp. Line up the ruler's 28-centimeter mark with the edge of the box.
Is this all number 2?
That was 2. Now I'm starting on 3.
So what's that?
Yes. Put a piece of tape. Before. Bless you. Those of you in the front, I need you to scatter out or something because I got to set up this lab. Y'all got to back up. Wired. Frozen colors. That's what it's actually called, frozen blue.
I'll be right back. Sit back patiently.
Come on, guys, I want to have time to do the lab. Y'all gotta hurry up. has a run short. To actually use the lab. Not gonna hurry. About 1 or 2 more minutes.
Paper. Body. Let's start. Stop. Reset. Perfect. Okay. You're a timer person. Allie, can you help me on any of my experiments yet? No? Okay. Okay, so it tells us it wants to measure from the bottom of the ramp upward. So 7 centimeters up means we're going to be starting the first one, 7. A little full time. So you're going to go right here. And we're going to tell you where to go. And let me explain something real quick. Okay? So you're going to pull your hair back. So Kimber can see when we started. You might need to get out of your seat. I need you to sit down, Haley. Started. Stop it. Okay. Start. Okay. So start. Tell her when. Oh, it could have been done. You gotta try it 4 times. Yes. you gotta do it again. Have to go down the ramp. Okay, since we had that first one that's so weird, we're gonna leave, this is why I had this big space right here for an outliner. So we're gonna redo this first file. Let's redo the first, let's have one more go at it. Now you're gonna start at 14 centimeters up when you put the line on. Okay, 14 centimeters up from the bottom. Got it? What was it?
381.
Okay. So this time you're gonna do it from 21 centimeters. And this time 28 centimeters. So it's gonna be right up there close to the tape. All right, I need as many people in their seats as possible. Guys, just our feet on the floor is enough to disrupt this rolling. This ball bearing is really particular to just people walking on the floor. Well, just us walking around the floor.
Oh, I get what you mean.
Is enough to disturb the ball bearing. Okay. Coming up. Try to keep the words down. That's enough. There you go. Perfect. Now let go.
Start.
Let's redo that one. Don't worry about the finger on what it has. Slow it down more.
Start. 314.
Guys, please stop moving around the desk. That's vibrating the floor.
Start.
Probably gonna redo it. Let's redo that one. Please stop moving around the chairs and desks.
Start.
Right now, let's redo this 314.
Start.
Between that. All right.
We copy that right here.
Yes, you're gonna copy that in your notebook and then I'll get the averages. All right, so the first one, don't need to copy the 10 seconds, 541, 529, 490, 606. Megan, I'm gonna take a picture and put the picture underneath the overhead projector. 541, that means 5 seconds, 41 milliseconds. 5 seconds, 29 milliseconds. 490 and 606. $490 and 606. I'm putting it under the projector. Can we please worry about this? Okay, here are the times. So please stop talking. Disregard this one. This was 7 centimeters. This is how we have our table set up. 7 centimeters, 14 centimeters, 21 centimeters, 28 centimeters. Remember, this is centimeters from the bottom. So this one we're not going to include. So we start with 5 seconds, 41 milliseconds, 5 seconds, 29 milliseconds, 4 seconds, 90 milliseconds, and 6 seconds, 6 milliseconds. I'll average it in just a moment. Our second release point, 14 centimeters, 3 seconds, 81 milliseconds. Trial 2, 3 seconds, 39 milliseconds. Trial 3, 3 seconds, 90 milliseconds. Trial 4, 3 seconds, 49 milliseconds. Then releasing from 21 centimeters from the bottom. 2 seconds, 54 milliseconds. 2 seconds, 79 milliseconds. 2 seconds, 94 milliseconds. And 3 seconds, 66. 3 seconds, 66 milliseconds. And then 28 centimeters from the bottom. 2 seconds, 44 milliseconds. 2 seconds, 94 milliseconds. 2 seconds, 29 milliseconds. And 2 seconds, 39 milliseconds. Okay. Let me average those.
I I didn't get to write them all down.
I'll give them just a minute for you, Megan, okay? That gets an average for 7 centimeters of 5 seconds, 42 milliseconds. At 14 centimeters from bottom, three seconds, 65 milliseconds. 2 seconds, 98 milliseconds for that average. Shade trip.
This is
Hunter. Can't get back. Oh, 252. Okay, here are these again, Megan. So 5, this is for the 7 centimeter row. 5 seconds, 41 milliseconds, 5 seconds, 29 milliseconds, 4 seconds, 90 milliseconds, 6 seconds, 6 milliseconds. And the average is 5 seconds. Is that 42 milliseconds, guys?
Yes.
5 seconds, 42 milliseconds is the average, the typical time value. And then 14 centimeters is 3 seconds, 81 milliseconds, 3 seconds, 39 milliseconds, 3 seconds, 90 milliseconds, and 3 seconds, 49 milliseconds. And the average on that one is 3 seconds, 65 milliseconds. And then 21 centimeters away from the bottom, it's 2 seconds, 54 milliseconds, 2 seconds, 79 milliseconds, 2 seconds, 94 milliseconds, and 3 seconds, 66 milliseconds, with an average of 2 seconds, 98 milliseconds. And then 28 centimeters from the bottom, it was 2 seconds, 44 milliseconds, 2 seconds, 94 milliseconds, 2 seconds, 29 milliseconds, and 2 seconds, 39 milliseconds, with an average of 2 seconds, 52 milliseconds. Okay. So looking at this bottom question, guys, what patterns do you notice in your data? I want you to answer that. You answer that on your own. What patterns do you notice in your data?
Can you go back to the fourth row, the third row?
Do you mean like? Is there anything else you need to write in the column that says 6%?
It says 6%. Where do you see 6%? What?
The one in the one square. Oh.
Here? No. But you do need to answer those reflection questions. They're on page 20 and 21. Analyze and interpret data. What patterns do you notice in your data?
Like, what do you mean?
What patterns do you notice? Which trials did not follow the pattern? We had some problems with that, didn't we? With that last set. So we had to do something to try to compensate, didn't we?
Yes.
Write that down. Then that final question, revisit the class prediction from lesson 6. So on lesson 6, we had a class prediction. It was when something moves slowly, there's less energy. Conversely, when something moves fast, there is more energy. So did our lesson today support that? Or did our lesson today go against that? Write your answer. You have 3 questions that you have to answer on your own.
I don't see it.
What? I've called out the answers like 5 times. Let's line up. All right, quiet. Quiet, quiet, guys. Straight line. Let's go.
Okay.